Okay, and let me share the screen. Okay. Okay. Hello, everyone. I'm Daniel. I'm the tech leader of Geomodelr, and welcome to this webinar. Today, I'm going to explain how the new export module works. This module will allow you to export the geological models from Geomodelr to the new version of MODFLOW, MODFLOW 6. This version was released in 2017 by the USGS, and all the information and files about MODFLOW 6 can be found in the official website of the USGS, like the release notes, binary executables, test problems, documentation, etc. Okay, there are several differences between older versions of MODFLOW and MODFLOW 6, but one of the most important is the discretization package. MODFLOW 6 allows you to create three kind of meshes. The first one is a regular layer mesh based on MODFLOW 2005. The second one is an unstructured grid. This grid is layer and is based on MODFLOW USG. And the third one is a fully unstructured grid. This mesh uses the same discretization structure of MODFLOW USG, but is not layered. That is, each cell can be connected with any number of cells in the horizontal and vertical direction. For example, in a layer mesh, we have to connect the cell number 8 with the cell number 9, just with the cell number 9 in the direction. But in a fully unstructured grid, you can connect the cell number 8 with the cell number 3 and with the cell number 6 and the cell number 9. So this mesh, by not needing layers, allows the user to control the number of elements in the mesh in all directions, regardless how complex the numerical model becomes. So you can control the size of the elements, and therefore you can do local refinements in places of interest without increasing the number of elements to a large extent. Really, this is a wonderful, a very, very wonderful feature of MODFLOW 6. Okay, let's start with the exportation. So this is the geological model that we are going to export to MODFLOW 6, including 7 wells. Let me show you the wells. Okay, this is you can see the 7 wells. 1, 2, 3, 4, 5, 6, 7. These wells are a borehole data set and 16 sets of rivers. You can see right here. Let me show another thing. This is the river that we are going to use in our exportation. If you want to know how to create a model, a geological model in Geomodelr, I invite you to visit our blog and see our older webinars and tutorials. So if we want to export this model to MODFLOW 6, we have to go to the main page of our model, of our study. We have to click on the export page button. And here we have 3 options to export: MODFLOW 2005, MODFLOW 6, and FLOPY. We click in MODFLOW 6. Okay, here we have 6 parameters to edit or select per each geological unit. First one, active or inactive state. This option allows us to set which units we want to take into account inside the numerical model. The second one is confined or convertible unit. Unlike MODFLOW 2005, MODFLOW 6 is able to treat each cell of the model as confined or convertible type. A confined cell is one which transmissivity is constant throughout the simulation, regardless whether or not the calculated head is in the cell is above or below the cell top elevation. For confined cells, drying and wearing options are not active. On the other hand, a convertible cell is one which transmissivity varies during the simulation based on the saturated cell thickness. The uppermost geological units should be selected as convertible because they will contain the water table. The other parameters are the hydraulic parameters. These parameters correspond to the horizontal hydraulic conductivity, horizontal anisotropy, the vertical hydraulic conductivity, and the new one, the maximum thickness of the unit. This parameter discretizes the geological unit throughout vertical direction, like a stagger cell. So I'm going to load the parameters of previous run. So we have inactive unit, the K1F inactive, and we have two confined geological units, KLT and the K1, K2U geological unit. After defining these parameters, we set the cell size, the size of the elements. We select the shapefile of the domain from the file repository. If you don't want to select any shapefile, Geomodelr defines the entire bonding square of the model as domain. So I'm going to select the domain shapefile. The bottom value is this value. This parameter is not mandatory. If you want to use the current bottom, you don't have to write anything in this for this parameter. So I'm going to set equal to 1. The current boron is 0, but I'm going to change to 1 meter. Finally, we select the rivers using a shapefile, our rivers, and the wells are taken from the boreholes dataset. I have to select the ID, the label of the rivers. We have to define the river and well edges size. This is the size of the elements around the rivers and around the wells, and the influence radius. These parameters has the same meaning of FLOPY, of our module export to FLOPY. So I'm going to set to equal to 40 meters, and influence radius is equal to 700. The same for the well. So we have to, I forget to write the name. For example, MF6 tutorial. So the only that we have to do is click on submit. So this our model is running. The meshing process takes a few minutes, so I'm going to download a previous running that has the same parameters. So I'm going to click in download file, and we have to wait a few seconds to get the files. Yes. I'm going to explain later. I'm going to explain the meaning of the influence radius in our model. So 31, 11 seconds. Okay. And 1 second. Okay. It's done. I'm going to move this file to another folder to put it here. And have to update. Okay. This is our. So, Geomodelr exports three types of files. The first one is a set of files that correspond to all data about MODFLOW 6 model. I'm going to explain these files or packages later. For example, we have the the ECU file, the IC file, the IMS files, the classical NAM file. So I'm going to explain them later. The second files group correspond to JSON files that include this is the JSON file, this one, and this one. These files include the set of cells ID for each geological unit, the well names, and the river names. And the last group corresponds to a VTK file. This is the VTK file, and an XML file. So the VTK file contains the mesh, the rivers, wells, and hydraulic parameters. And this file is used just for visualize in Paraview. So the XML file has the same color map. What is that right here? Has the same color map of the geological units in Geomodel, and this file is loaded from Paraview to visualize the geological unit. The color of the geological unit, the same colors of in Geomodeler. So I'm going to open Paraview. And I'm going to import our ML6 model. I'm going to export the VTK file and click and apply. You have to wait a few seconds because this file contains many information about our model. Slowly. So this is our model. So for example, here we can see the hydraulic conductivity in the X direction. Click right here, and this is the data that we have to this model. For example, this is the hydraulic conductivity in the X direction. We can change the color map. Clicking here in edit color map. I'm going to use the log scale and click, and this is the the hydraulic conductivity in the X direction. I'm going to change to this is the hydraulic conductivity in the Y direction. Let's change to log scale. And this is the hydraulic conductivity in the vertical direction. Also, Geomodeler exports the data about which cells are convertible or confined. Right here, we click and select convertible. So one corresponds to convertible cells, the red cells are convertible, and 0 corresponds to confined cells, the blue ones. Furthermore, we have pointed all the river and well cells just for visualization purpose. For example, we can, oh, sorry, to delete this. We can select right here rivers. Here we can observe the cells that correspond to the rivers. So I'm going to use a threshold filter to get only river and well cells. So we click filters, common, and threshold. So a value equal to zero corresponds to not river cells, and greater than 1 corresponds to river cells. So I'm going to change the minimum to 0.1, and the maximum is, oh, sorry, we have to select rivers, and the maximum is 16, and click and apply. So here we have the cells that correspond to rivers. I'm going to activate the grid, click right here in surface and select surface with edges. So I'm going to change the color of the edge to black. So we can observe the cells that correspond to the rivers. Now I'm going to create a filter, a threshold filter to get the well cells. So we have to click in the model, filter, common, threshold. We select wells, wells. Here, we select 0.1 because zero value correspond to non-wells, not well cells, and greater than 1 correspond to the wells. So we click and apply. And here, I'm going to change the color of the rivers at the wells to wells and activate the grid. So here we can observe the mesh of the rivers and the mesh of the of the wells. So finally, let's visualize the geological units. I'm going to turn off this and turn on the model. I'm going to select the units. So this is not the real colors of the geological model. You can remember. But yeah, this is our model. Going to turn on the rivers. So this is the our model in Geomodelr. So I'm going to load the XML file to get the real colors of the model. Clicking right here in choose preset, options to load. So sorry, um, we have to click in import. We click in our XML file of the model and click in apply. So this is our model in Paraview, and you can compare it with the real model in Geomodelr, and you can see it's the same model has the same colors. So let me activate the just the grid. Prefer a black color. So we can, for example, see the discretization in the topography in the top of the model. Geomodelr use a Voronoi cell grid approach to build the superficial mesh. So, for example, you can see too you can see the smooth change of the size of the cells of the this is the cell the size cells of the model. This is the cells of the model, and this is the cells of the rivers. So you can see how the smooth change between the size of these cells to these cells, or from these cells to this cell. For example, if you remember, I use a 300 value to the cell size, so the approximate value for the edge side of the cell is 300, and the for the river, for example, this is a river. We check to this line. For example, the side of the river is equal to 40. So the influence radius is the distance between the river and the model to start to change to the cell size from 300 to 40 to 40. So it's the same, has the same meaning of to the wells. For example, this is a well right here. For example, this is a well. So the influence radius is equal to 700. So from the well, we create a radius of 700. So the units, the cells of the model change the size from 300 to 40 from a distance of 700 meters. So this is the meaning of the influence radius. So okay, so um, if you remember, like I said before, there is no the concept of layer. There is no concept of layer in a fully unstructured image in MODFLOW 6. So, for example, it allows to connect a cell with several cells in all directions. You can see, for example, let's look for a cell. For example, this cell is connected just with this cell in this direction, and is connected to this cell and this cell in that direction. So this is a powerful feature of MODFLOW 6. So, uh, oh, sorry. We're going to run our model, but I'm going to explain how to run the model. But before that, you have to know one thing. What is the thing? Actually, Model Muse, if you know Model Muse, is the USGS graphical user interface for ModFlow supports structured layer grids and unstructured layer grids based on quad tree approach. So, unfortunately, there is no ModFlow-based model software that supports 3D unstructured visualization of ModFlow 6. So we are going to go, we are going to load, run, and post-process our model using FLOPY. FLOPY is a Python library that supports a Modflow-based model and includes Modflow 2005. Includes Modflow USG, Modflow 6, etc. Okay, so this is our Python code. We also need to use the NumPy library, the VTK library, and JSON library. So here we import our libraries: NumPy, FlowPy, VTK, and JSON. So okay, here we set the name of our model. We set the location of our model, where the folder that contains all the files of our model, and we set the location of the Modflow 6 executable. You can download this executable from USGS website. Then here we load the simulation, and we can observe all the packages that contain the simulation and model. The simulation is the highest level component of the simulation. This one is the simulation is the highest component of Modflow 6, and it can include multiple models. This model can be connected by flow by cells, or they can be independent. Okay, the remarkable package of the simulation component are the time discretization. This is the time discretization package that contain all the information about the time, about the discretization time, and the IMS package, the iterative model solution. I will explain this package, the IMS shortly. On the other hand, uh, we, we, we export just one model. So this model contains this package, the DISA package. This is the unstructured discretization. This file contain the discretization data like nodes, cells, the connection data, all the data related about the discretization. The RIP0 package. This is the river package. This package contains all the information about the rivers, the nodes, the hydraulic parameters. The well package, this one, contains the information about the wells, like nodes, the hydraulic parameters. The MPF package, this is the node property flow package. It corresponds to the hydraulic conductivity, the cell type, confined or convertible, wet dry options, etc. The IC package, this is the initial condition package. It contains the initial head for example, for transient models, or the initial iterative head for steady state problems, our case. And the OC package, this is the output control package. Yes, this file determines how and when the heads are printed. So the first one, the DISA package. If you remember, this package contains or has all the information, all the data about the discretization, about the mesh. For example, we can observe, or we can list the cell information. This is the data about the cell. For example, this is the cell number 0. This is the ID cell. This is the center of the cell in X and Y coordinate. This is the number of vertices of the cell, and this is the vertex ID to define to create the cell. So we can observe right here vertices information. This is the number, the ID of the vertice of the node. So yeah, and here we can observe the coordinate of the node. Here, this is the JA array. This is the array that contains the connection information in the model, how the cells are connected between them. On the other hand, we can check the river package. Uh, by default, Geomodel exports the river's data, for example, the stage, the conductance, and bottom of the rivers equal to 0. Right here, you can see this is 0. This is the node. This is the stage. This is the conductance. This is the bottom, and this is the name. And we change the real names. The names are enumerated like river 0, river 1, river 2, and so on. We do this because MODFLOW doesn't allow to use non-ASCII string for the name of the river, for the name of the wells, for the name of the model. But if you remember, we export 3 JSON files, and one of them, the river's name JSON file, contains a dictionary where the keys correspond to these enumerated names: river 0, river 1, river 2, and the value of the dictionary is the real name, the name that came from the shapefile. So we can use this file and load it to update the real names or update the real parameters. For this example, we're going to use the top of the river cells to define the river parameters. For example, the stage is equal to top minus 0.5. This means that the stage of the river is located a half meter under the topography. The conductance is equal to 30 for all rivers, and the bottom of the river is equal to top minus 2.5. So that means that the bottom of the river is located 2.5 meters under the topography, or the depth of the river is equal to 2 meters. So this is how the updated river package looks like. This is the stage, topography minus 0.5. This is the conductance equal to 30. This is the cell ID that corresponds to the river. And this is the bottom of the river. If you remember, top minus 2.5. And this is the real name, the names that came from the shapefile. So, okay. The well package, we do the same. We have the node, we have the volumetric well rate, and we have the name. We set the volumetric well rate equal to 0, and we create enumerate names. It means that we have well 0, well 1, well 2, well 3. For the same reason that we do in the we did that in the river package. So we have another JSON file, wells name JSON file. We can load this load this file and update the names, and we can use the names to, for example, define or set the volumetric well rates. We do this in this part, so we can observe how the updated well package looks like. We update it to the real names, and we set for each well the volumetric well rate. So the IMS package. This is a very, very important package because it's the iterative model solution, and this package has the data about the numerical solver. For example, we can observe here all the information of the package, all the data that the package has. For example, Geomodelr by default export the nonlinear iteration equal to 50 and the linear iteration equal to 30. So we are going to change these values to 500 and to 130 respectively. So another parameter is very, very important, is the complexity. This is a keyword. This is the complexity. This is a keyword that defines the default nonlinear and linear solver parameters. By default, we export this parameter equal to simple. This means that model is closer to have a linear behavior, but remember we have several convertible cells, so we change it to moderate. So because this means that our model is not linear. Okay, the Newton-Raphson solver. The Newton-Raphson formulation is a solution, a numerical solution scheme that it is useful for complex problems that involve, for example, water table conditions or convergence problems because of wetting or and drying cells. So we are going to activate the Newton-Raphson solver, and we are going to use the under relaxation option. This method is an option that can increase the convergence for highly nonlinear models, like our model in this case. On the other hand, we activate the by conjugate or the big step gradient method because the Newton-Raphson method generates an asymmetric matrix. So we are ready to run our model, but first we have to write the simulation with the new data and run the simulation. So the simulation takes 15 minutes. And, and okay, so now we are going to load the result, the heads of the cells, and we are going to save it or write it on our VTK file. To do this, the hydraulic heads data are saved in the HDS file. We can get this data using the output keys command. So we know we can see right here. This is how we can get the data of the heads. So we get the data of the heads or the first stress period. So so it should be noted that then when the Newton-Raphson method is used, no cells will set as inactive or dry. So because Newton-Raphson applies a quadratic smoothing approach to compute a saturated cell fraction to allow a smooth transition between wet to dry cells or dry to wet cells. Consequently, we have to point out all cell where head is below his bottom. So we are going to create this array, the dry cells. Then this array is equal head minus bot. So this array allows to know which cells can be considered as dry. For example, if dry cell is lower than zero. Now we are ready to load our VTK file. We create a reader, unstructured VTK reader. We load our simulation, our VTK file, and we add the heads and we add the dry cell. So after that, we save our VTK file with the new data. Before to see the results in Paraview, we are going to talk about the last JSON file. This file contains a dictionary where the keys are the geological unit names and the value in this dictionary correspond the ID elements of the mesh. This is a very important file because the user will be able to know what are the corresponding elements of one geological unit. So they can change or they update the hydraulic parameters according to the geological unit. So, okay, so we have to return to Paraview. So we have to update our visualization in Paraview to upload the new data, but I'm going to import another model where the data is the heads are in that file. So I'm going to open MS webinar and apply. This model is the same, but we have the heads and the dry cells data in this model. we have to wait a few minutes, a few seconds, sorry. So here we have our model. I'm going to import the head. Click on head. So I'm going to change to the classical rainbow color map right here. I can click on close. So I'm going to create another threshold filter using the dry cells. So we click on filter, common, and threshold. So we select right here dry. The maximum value is the largest value, and the minimum value, for example, I will use a value equal to minus 10. This means that I will see only the cells where the head is below 10 meters, the bottom at most. So we click on apply. I'm going to close this and I'm going to rescale the data range. So here we can observe the results of our model. For example, in this part, this is the rivers. In this part of the model, the water. So the water is flowing into the model from the river into the model because river heads are over the water tables. And on the other hand, for example, in this part of the model, right here we have rivers. In this part the rivers are working like pumping wells because water table should be over the river stage. So we can let me show you the surface so we can analyze, so we can check our model, the grid model, and the results on right here. So okay, we have finished with our exportation and this webinar. I invite you to read and learn more about MODFLOW 6 and its properties. You will discover that this new version of MODFLOW is a powerful tool to create and simulate groundwater models together with Geomodelr. So thank you to be with us in this webinar. So do you have a question for us? Give me a few seconds, please. Hi.
Okay, so this was the webinar of MODFLOW 6. Now it's available, the platform for you to use. If you have a user in the platform,
I have to share the screen.
if you have a user in the platform, you can start creating 3D models and sharing them with your colleagues and working in teams, etc. You can also look at one of our plans. The plans of MODFLOW 6 are the plans of the Azure Geology, which allow you to export your models directly to MODFLOW, to vFlow, and now to MODFLOW 6 with unstructured support. So now I'm going to show you our website. Geomodelr.com. If you need any help, please contact us. Please write to us. You can ask us things at in the chat. Leave us your email, and you will have a really close answer. If you want to start creating 3D models in Geomodelr, just create the user here, signing up, or here up in Geomodelr. We have more than 2,500 people modeling the planet with Geomodelr. Thank you very much for coming to our webinar.